Hi, my name is Abhishek Malhan. Along with my teammates Ayush Agarwal, Nabil Kazi, and Prabhav Solanki, I entered into a competition on Driven Data. Driven Data is a website which hosts a lot of machine learning and artificial intelligence based competitions. Now let's look on to the details of the competition. Now let's talk about the details of the competition. We can see on the homepage that the competition has many submissions that have been made. Moving on, let's talk about dengue. Dengue fever is a mosquito-borne disease that occurs in tropical and subtropical parts of the world. In mild cases, symptoms are similar to the flu, that are fever, rash, muscle, and joint pain. In several cases, dengue fever can cause severe bleeding, low blood pressure, and even death. Because it is carried by mosquitoes, the transmission dynamics of dengue are related to climate variables such as temperature and precipitation. The dataset comprises of the environmental data collected by various US federal government agencies. Our task was to predict the number of dengue fever cases reported each week in San Juan, Puerto Rico, and Iquitos in Peru. Now moving on to the data preprocessing. Our dataset had been provided from Driven Data, which had 1457 training samples and 417 testing samples. We imported the data and performed elementary data analysis, that is EDA, using head, info, and describe functions. Then we moved on to the visual EDA. We plotted the number of cases in San Juan versus Iquitos. We plotted the cases versus year to understand the data distribution. We did the plot of year, city, and count, the bar plot of year versus total cases, the total count plot of total cases, the data distribution of each feature, that is the histograms. We also worked with strip plot and LM plot of various features with each other.
Hi, my name is Prabhav Solanki and I'll be telling you about the approaches we used in our project and why we used extra linear trees in the last. So basically we started from linear regression, but we couldn't find any linear relationship amongst the dependent variables and the independent ones. So we basically moved to lasso and ridge, which are just the regularization of linear regression. So basically they couldn't also give us any proper trends and any better accuracy. So we moved to elastic net, which just balances the lambda 1 and lambda 2 values, and it also obviously failed to give us any proper trends. So we moved to svm.svr and linear SVR. As you know, SLR, simple linear regression, couldn't give us any non-linearity in the project. So we basically chose SVR then, and we hoped that it would give us some non-linear trends. It obviously did, and these trends were proper, and it gave us a good accuracy. But then we wanted even higher accuracy, so we moved to decision trees. So decision trees was working quite good and gave us really good trends and really good accuracy. But decision trees are good for working on small data set, as you know, and our data set was quite large, so we wanted even something better. So we then thought of using random forest and extra trees. Then let me introduce extra trees for you right now. So extra trees is just extremely randomized trees. It takes data in a very random fashion, so basically which makes them more consistent and more flexible. There is no biasing and no overfitting as well. So basically this helped us, and we used extra trees over random forest because of its advantages. And then we could find that okay, as it's an ensemble learning technique which combines the decorrelated decision trees collected in a forest to combine their outputs and give a classification output in the last. So it could give us better accuracy and very good trends in the last. So that's it.
Due to the non-deterministic results obtained from the data analysis, we had to try out a bunch of machine learning algorithms, which included linear regression, lasso regression, ridge regression, elastic net regression, support vector regression, and then we also went for decision trees, random forests, and extra trees. Now, in our case, the extra trees performed quite well as compared to the other methods. Now, reason, as I already mentioned, extra trees for our dataset perform the best. Extra trees is the term used for extremely random trees, and this method is much more flexible than the random forest. As random forest is greedy in nature, whereas extra trees allows random feature for splitting the data, which makes it much more consistent and avoids overfitting. Extra trees approach exhibits a non-exhaustive nature, and they are much more faster than the random forest method. The reason behind that is when a random forest is built, a greedy approach is used. But whereas when extra trees are built, they use a random feature to split the data. That's the reason why they are more consistent and have much less variance as compared to random forests, as they do not overfit. After the hyperparameter tuning of the extra trees using the grid search, the results obtained were quite good, and we reduced the error to approximately 18. Moving on to the evaluation metric, we had to use mean absolute error, as it was one of the clauses of the competition, and the final value we obtained using the extra trees after the hyperparameter tuning was around 25.1. Talking about the mean absolute error, for mean absolute error, we calculate the difference between the true value and the predicted value. Then we sum it for all the instances, and in the end, we divide the whole value by the number of instances that are there, or the number of records. Let's understand what mean absolute error actually is with the help of an example. Now suppose the scale states that you're 90 kgs, but in reality you know that you're 89 kgs. Then the scale has an absolute error of 90 minus 89 kgs, that would be 1 kg. As I already mentioned, extra trees for our dataset perform the best.
Hi, my name is Ayush Agrawal, and I'll be speaking about the technical details which we have faced during this project. Here are the details of the following. We faced a couple of challenges. First, the dataset was quite small, and general machine learning algorithms are quite data hungry in nature. As you can see, the 4 features over here, city, year, week of the year, and total cases, just have only 1456 records, which is quite small, and we have to tune the hyperparameters quite a lot to obtain a good result. We had to tune the parameters to obtain a good result, we run a couple of hyperparameters mentioned over here: the learning rate, n estimator, max depth, criteria, max features. As you can see, it took a lot of time for a lot of iteration. So we had a limited computational power, and we could only try out a limited number of values for each hyperparameter. Secondly, the results obtained from data analysis weren't deterministic, and that we meant we had to try a bunch out of algorithms to obtain a good result. On driven data, we submitted 3 submissions. In the first submission, we were able to achieve a score of 29.2. In the second submission, we got a score of 27.49. And finally, we submitted and we were able to achieve a score of 25.1 MAE, which brought us to a rank of 810 out of 7,434 competition. This is among the top 11% we were able to achieve using our model. Thank you for listening.